Okay, so now we're going to look more into an electron. Okay, so if an electron reacted just like a wave, like only a wave and had no mass, if you had a particle beam of electrons right in here, so we were shooting electrons through here, if it acted just like a wave, you would only see, two slits coming through here. I'm sorry, if it acted just like a particle, because only everything, it would be blocked by everything else. It could only go through the two slits, okay? But what they found is that you didn't just see two slits of, light, you saw many slits of light, which was pretty amazing. So they realized that these electrons were bending through. Okay, so basically electrons act as a wave and as a particle, just as we were talking about before. So because of this, just like light, we can calculate the energy and wavelength of an electron. Remember, the big difference between it is that electrons have a mass. Okay, so here is the wavelength of a electron. So remember, we have a wavelength of light, and now we have a wavelength for an electron, and the big difference is the mass right here. So in a question, if it says what calculate the wavelength of light, you're going to use the wavelength of light formula. But if it says to calculate the wavelength of an electron, you will use the wavelength of electron formula. And the big difference again is that mass formula there. So let's actually calculate a wavelength. So it says calculate the wavelength of electron traveling with a speed of 2.65 times 10 to the 6 meters per second. Okay, so if we look at here, we draw this. The formula for wavelength for an electron, wavelength equals to Planck's constant divided by mass of an electron times velocity. Planck's constant is a constant, and we know this is 6.626 times 10 to the negative 34, and the units are kilograms meters squared per second. This is an H. Mass of electron, this is a constant. Electrons always weigh the same amount, and they weigh 9.11 times 10 to the negative 31 kilograms. So very, very small. And then the velocity in the problem was given to us as 2.65 times 10 to the 6 meters per second. So if we look and make sure our units are correct, we have kilogram and kilogram, so that's good, those are the same. Meter, meter, seconds, seconds, they all match up. Now do you see this is a meter squared, so there's two of them. So our final unit, since there's only one down here, will be in meters, because there's going to be a meter left over. So if we plug everything in, wavelength equals Planck's constant, 6.626 times 10 to the negative 34, divided by the mass, 9.11 times 10 to the negative 31. Okay, and our velocity, 2.665 times 10 to the 6th. Okay, so if we multiply that all out, you should get 2.74 times 10 to the negative 10, and that is going to be in meters. So that is the wavelength of that electron, okay? And now on this question, they could ask you, they could calculate two things. They could give you a velocity and say to calculate wavelength, like we did here, or they could give you a wavelength and say calculate velocity. But either way, you're just using this formula and solving for an unknown. Okay, now since we can calculate wavelength, we can also calculate energy. Okay, so we have two formulas for energy depending on what we're doing. We already talked about that. So this is this is an energy. So if you want to find the energy of a photon, so remember when you excite an electron, the electron goes up and then comes back down and then releases a photon to do that. And when you do that, you can calculate the energy of the photon release. So do you see here? This is the Rydberg constant for hydrogen. So it's every atom has a unique constant, but they've actually only been able to calculate it for hydrogen and helium because the calculations get so complex that they haven't been able to basically figure them out. But we can look at the exact energy of a photon for hydrogen and helium using this equation. So Rydberg constant, this is the constant for hydrogen, 2.17 times 10 to the negative 18 joules. Okay, so here's the formula, put that in. And then energy between both levels. So this is going to be your higher level and your lower level. So let's look at a question to see what I'm talking about here. Okay, oh, and then here's the formula that puts wavelength and energy together. So you can see that wavelength and energy are associated with each other. So as wavelength, actually make this bigger because you're not getting your equal sign. Nope. Okay, as wavelength is longer, energy is lower, and as wavelength is shorter, energy is higher, just like with light. Okay, so here it says determine the wavelength. So we're going to have to use this formula here of light when an electron in a hydrogen atom makes a transition from 5 to 6. Okay, so let's just draw what this is first. Okay, so we have this hydrogen atom right here. Okay, and we have orbitals around it. Orbital, let's see, that's 2, 3, 4, and it says we're looking at 5 and 6. Okay, so let me change my color. Let's do blue. Okay, so I have an electron right here in level 5. Okay, I'm going to irradiate it with light, okay, which is going to excite the electron up to level 6. So right now it's on level 5, and this is level 6. If you just count out 1, 2, 3, 4, 5, 6. I'm just counting these here. Okay, so it's going to excite and go up to the next level, but then it wants to come back down. But as it comes back down, it has to release that energy, right? Because the energy is all the way up here. Now you have to go back down and release it. So it's going to release that photon of energy, and we want to find the energy related to that photon. Okay, so we can actually calculate that by hand. We don't even have to do an experiment because we already know. So let's look at the, let's draw this formula here. So we have energy will be negative RH, this is that constant right here, multiplied by 1 over n squared of the upper level. So these are your levels, we're looking at 5 and 6, minus n squared of the lower level. Low. Okay, so let's plug our numbers in. RH is, let's see, I just had that, 2.17 times 10 to the negative 10 joules. Okay, our R of the upper level is 6, or I mean our N, okay, and our lower level is 5, because we're just looking at 5 and 6, so this is the lower number. So we plug this in, energy equals to minus 2.17 times 10 to the 10. Oh, and notice these don't have units, but this does, so our final unit will be in joules. So 1 over our upper level, which is 6, so we're going to do 6 squared, minus 1 over our lower level, which is 5 squared. Okay, so if you plug this in and you calculate it, you should get energy is, let's see, 2.65 times 10 to the negative 12 joules times. Okay, that's not what the question asked. It didn't want the energy, it wants the wavelength. So we're almost there. So we have the energy, so that's how much energy that photon releases. So that energy is worth, or that photon is worth that much energy. But we want it in wavelength. So we know that wavelength equals to Planck's constant times the speed of light over wavelength. Okay, so we can get the wavelength. So this is the connection between energy and wavelength. They'll do this a lot in the homework. Sometimes they'll say, we just want energy, and they'll give you the upper and lower levels, so you just stop here. But if you want wavelength, you go to here. You use this formula if you have the energy. So this is a connection. So anytime, sometimes it's a two-step problem like this one. So we know Planck's constant is, or let's go ahead and plug it all in. Energy. Let me change the color too. Let's do this kind of yellowish color. Energy equals to Planck's constant, so 6.626 times 10 to negative 34. That's in here, and then 3 times 10 to the 10th meters per second, and then we have wavelength. Okay? And we know our energy, our energy is, let me just erase that, is 2.65 times 10 to the negative 12. Okay? So we have this, and we can solve for wavelength. You need to bring your wavelength over first. Basically, these two will switch doing the algebra. This will come over here, which will cause this number to move there. So our wavelength will be 6.626 times 10 to the negative 34 times 3 times 10 to the 10th divided by 2.65 times 10 to the negative 12. Oh, sorry, this is not 10, this is 8. Because we're doing meters per second, not centimeters per second. Okay? And so when you do this, you get 6.626 times 10 to the negative 34. That multiplied by 3 times 10 to the 8. Okay? And you divide that whole number by 2.65 times 10 to the negative 12. And I get 7.5 times 10 to the negative 14. And that's in meters. Alright, so that's how you do the problem. And so here, this energy tells us, this formula here, how much energy it requires to go from level 5 to level 6. You could also do this from, let's say level 3 to level 4. Okay, so you can do this for any energy level. And you could get the energy associated with that, and then from there you could get a wavelength if you want. Let me check something really quick. Yeah, it is 3 times 10 to the 8th. Okay, just want to make sure. I thought it was. I always get the 3 times 10 to the 10th and 8th mixed up. Anyway, coming back to where we were at. So now we can see we can calculate the wavelength of an electron, and we can also calculate the energy, the photon released when that electron is excited. Now there's an uncertainty principle, okay? And basically what this says is that we're actually uncertain where electrons are. So the velocity of electron is related to the wave nature, the position of electron is related to the particle nature, but basically the Heisenberg uncertainty principle says the more accurately you know the position, the less you know about the velocity. So long story short, we really don't know a whole lot about electrons, about the velocity and the position. So either you can calculate the position, kind of where it's at, but you don't really know how fast it's traveling, or you can calculate the velocity, but you don't really know where it's at. Anyway, so the location of electrons basically is really hard to calculate its exact location. They're moving so fast you can't really pinpoint, a point in space. Anyway, so it's uncertain where electrons are exactly. So basically we can look at a statistical nature of it. So this is a good example here. Like pitching a baseball, okay? If we're looking at the trajectory, okay, well, this is more like a softball. So if we're pitching a softball in the air, it makes this arch here, okay? Statistically, we know at any point in time, it'll be somewhere in this archway, right? And that's about what we could tell about electrons. We don't know exactly where they're at, okay, but we can kind of get an area where they're at, the most likely position. Okay, so what we're going to look at is what's called orbitals in our next podcast. So for example, one of the orbitals looks like this. It's sphere. Okay, so it's 3 dimensions, so it's sphere. So we know electrons are going to be somewhere in that sphere more than likely, okay? And that's an orbital. So an orbital, we'll look at it more, is basically a statistical picture of where you're most likely to find an electron. Okay, so that's what we're going to look at next. Where's the location? Because that's important for bonding, right? We're trying to look at and study the bonding of different elements, and to do that you have to know what the location of the electron, or at least an idea of it. So we just calculated the wavelength of an electron, okay, and the energy of a photon release when an electron's excited.